Hi, my name is Lyle Kim. I'm a fourth-year PhD student in the computer science department. Today, I'll talk about fast quantum state tomography via accelerated non-convex programming. And this is joint work with Dr. Amir Kalev at USC, Dr. George Kollias and Ken Wei at IBM, and my advisor, Professor Anastasios Kyrillidis. So just like in building classical computers, just like electrical engineers use multimeters and oscilloscopes to verify that electrical circuit works as expected, we need similar verification tools in building quantum computers. And quantum state tomography is one such tool. So on high level, we have this quantum state row, and we're going to prepare the same quantum state in this quantum computer, which is going to produce a bunch of measurements. Using those measurement data, we can reconstruct an estimate of the original quantum state, and we want to see if that's close enough to the original quantum state we had in mind. Mathematically, we can write the quantum state tomography objective as follows. Here, calligraphic A is a particular sensing matrix, and the ith component of the calligraphic A of rho satisfy this trace quantity, and this is called the expectation value in quantum computing, and it's highly related to how quantum computers actually take the measurement. Y can be thought of as a vectorized form of the measurement data, so it's going to include both of zeros and ones. This PSD constraint and the unit trace constraint arise naturally as the definition of quantum state, which is expressed as a d by d dimensional complex matrix. So this optimization problem is notoriously hard to scale, and it suffers from two main bottlenecks. First one is with respect to optimization. So our variable of interest rho, which is a d by d dimensional complex matrix, grows exponentially in terms of the number of qubits. And secondly, in terms of the amount of data, so we have this linear relation, calligraphic if A of rho equals Y, which is why we have this least squares objective. So theoretically, if we have enough access to enough data and enough sensing matrices, then we can just invert this and obtain this rho. But how would these scale? So only for 16 number of qubits, our variable of interest is more than 60,000 by 60,000 dimensional complex matrix. And also to utilize this kind of linear inversion intuition, we need d squared number of measurements, and d self-grows exponentially with number of qubits. So only for 16 qubits, we need more than 4 billion measurements. So to handle that, we're going to use low randomness as our prior information. So here I'm plotting four different quantum states. So for example, if you look at the GAC state, only the four corner entries have non-zero entries. So this can be written as a low rank matrix. And similarly, we can write these two matrices as low rank. And we also use random matrix to see the robustness of our method. So we're going to use low rankness as our prior, which is our additional constraint. In which case, when you have low rankness and the PF constraint, it's been shown that you can ignore this unit trace constraint without affecting the final solution. So having this low rank constraint gives us the ability to apply something called compressed sensing, which pivotally relies on this assumption restricted isometric property, which is a property on the sensing matrix. But the previous literature by David Rose proved that one can reconstruct a rank R density matrix rho using R times D times polylog D measurements. And that reminds that without any prior information, you need D squared measurements. So if R is much smaller than D, then you can reduce a lot of measurements to reconstruct this density matrix rho. And Lyle showed that a particular sensing matrix that's actually used in quantum computing does satisfy this RFP. So it makes sense to utilize compressed sensing, and that's how we deal with the amount of data. And then with respect to the optimization, we have this modified objective function. So to typically to solve this kind of constrained optimization problem, you need some projection mechanism onto the subspace of the constraint subspace. Here, the PSD constraint is convex, and low rank constraint is actually non-convex. And to project onto these subspaces, you need to perform singular value decomposition on rho on every iteration, which is prohibitively expensive when D is large, and D is almost always large for this quantum state tomography. So instead, we propose to reparameterize this rho as a UU transpose, in which case we can rewrite this objective function as an unconstrained optimization problem. And we have two motivations. The first one is now our variable of interest is U. So it's strictly in it's in the strictly smaller space than the original space. And again, we don't have to project onto any constraints because now we have unconstrained optimization problem. So how do we solve this kind of vector objective? We can apply gradient descent on this vector u, which is called vector gradient descent. And in this paper, we propose momentum-inspired vector gradient descent, which is an accelerated variant of this vector gradient descent. So we have this quite complicated structure. So we have non-convex constraint, which makes the problem non-convex. We applied this factorization and we modified the objective function. And then we're going to apply this acceleration technique. So that results in very complicated theory. But essentially, if you initialize according to this, and if you set up your step size, eta, and momentum parameter according to our theory, then you achieve something called accelerated linear convergence rate. We have extensive experimental results on the paper. So these are different number of qubits and different quantum states. Essentially, the main message I want to convey is that our theory uses this value of mu star, which is very small, but in practice, you can use much larger momentum value and achieve much faster convergence rate in all cases. In the main paper, we have more complete theory with better explanations. And we actually provide this open source software of this method that's compatible with Qiskit so that quantum engineers can actually use our method. And we have extensive experimental results using real quantum data that we obtained in collaboration with IBM. Please come to my poster session for more details, and thank you for listening.